be starting. Okay. Great. Before we proceed to today's contest, I would like to come back for one particular task to the contest 2 days ago. Because I always skip a few tasks like during the problem analysis, so that we can proceed to something a bit more interesting always. But there was one task that none of the teams managed to solve. I don't think that anyone even tried it. No one even tried this task. And this could be a bit surprising because this task is not as hard as one could expect. And that's why I would like to first come back to one task and then we can proceed to discussion of yesterday's conference. So the only task that I wanted to come back from this Polish team championship in 2011 was the problem about bits generator. Maybe I will recall the problem just briefly so that everyone remembers what I'm really talking about. The problem is bits generator. This is from Wednesday. We just come back to one particular problem. And so in this problem is a bit mysterious at the first sight. We are considering a pseudo-random number generator, bits generator, and it works like this. It starts with a seed, Z, and it iterates the following process to generate bits. So, like the function generate bit, works as follows. We take this initial value of this seed, we perform any arithmetic operation on this, like whatever, divided by k, or modulo m, whatever, a random function here. And then if z is smaller than n divided by 2, I just have to copy the code, then we return 0, else we return 1. And every time the z is in the interval from 1 and minus 1. All the time that happens. So we have this very simple bits generator. We start with a seed, and then just we perform this magic operation on z. A, c, k are some constants, and then we return the next bit depending on if z is smaller than n divided by 2 or greater. And our task is we are given a sequence of bits. So the goal is we are given a sequence of bits v1 up to vn. And we want to find out whether there is an initial value of the seed for which this sequence can be generated. So, does there exists z for which this sequence is generated? This is the question. And if so, how many initial values of C there exist? And the constraints are n is at most 100,000, I guess, and m is at most 1 million. So this problem looks a bit mysterious. It's not really clear what is this pseudocode happen, what happens here. But it actually turns out that it's not important what happens here. The important thing to look at this problem as a graph problem. So we have all these possible values of the seed. We can actually enumerate all of them because the number is not that large. And for each of the value of the seed, we know which is the next seed performed after a single generate a bit call. So for instance, seed 0 could be transformed to seed 7, seed 7 could be transformed to seed 9, and so on. Each seed is transformed into some other value of the seed, and in the meantime, a random bit is returned. It depends on, so for instance, q could be 0, q could be 1, q could be 0. It depends on the value of this. And this is how the graph is constructed. And first of all, we want to check if we have a graph in which every node has exactly one outgoing edge, because this is the case here. From one seed we just get to one other particular seed. Then how does such a graph look like? I guess that maybe you have at some point encountered like such graphs where each node has just one outgoing edge. It is like there's a collection of cycles, and each such cycle has some trees like attached to it. This is how such a graph looks like, and so on. There are a number of trees just attached to this cycle. And what are we really wanting in this problem? This is a somewhat pattern matching problem. We have some pattern, and we want to find this pattern on the sequence of edges. So for each node, I want to find out whether if I traverse this path along the edges, for instance here, whether this is just exactly this word we want to be in or not. This is just a pattern matching in a graph. In a very particular type of way. Okay, so this is the actual problem, and there are many pattern matching algorithms. I guess you know some of them, like Newton-Spratt algorithm, for instance. And you can try to solve this task by modifying the Newton-Spratt somehow, like taking into consideration cycles separately, trees separately, and so on. However, the real, like the simplest solution to this problem involves a very much easier technique. Meaning, we involve either something like string hashing, or we involve something like KMR algorithm, like where you, for each word of length which has a power of 2, I want to compute some identifier. So, how it works? What I compute in 2 steps. So, first of all, for each node, so for step 1, for all like nodes in G, let's write it like that, we don't really consider any seed or whatever, we just have a graph. So first of all, for each node, and for each I such that I in the range from 0 to ceiling of logarithm of n, because this is the exponent of the power of 2, which first exceeds this n with this length of the bit sequence that we are looking for. I want to compute an array jump from V to I, which means at what node I arrive when I jump 2 to the power of v positions from the node V. Where I arrive when I jump 2 to the power of I positions, like edges, jump edges from V. And it is extremely simple to compute such an array. Well, first of all, jump from V, 0, are just the outgoing edges. First of all, jump from V to 0 are just the edges of the graph. So we just jump along an edge of the graph and I know where I get. And then to compute jump from V to power I, what I do, I need to jump from the node, jump from top is V I minus 1. And again, so here I jump 2 to the power of I minus 1 edges, and I jump the other 2 to the power of I minus 1 edges. So actually computing such an array is very simple. And then I want to compute a second kind of array. this array will be assigning identifiers to the respective nodes. So I would like to have another array ID from V to I, which is some identifier of the path from V to jump Vi. So I take this whole path of length to the power of I, and then what I do, I just want to have some identifier to the bits, the sequence of bits on the edges. And actually, I do it very similarly. So these identifiers, I would like them to be small integers, so that I can compute them, so that I can compare them. The good identifier will be just the sequence of bits on the path. However, the sequence of bits can be very long. So what actually we do is just again the ID from V to I is just to 0 is just the single bit. This is the best identifier for the path, just consisting of a single edge. And for greater values, now I will be computing everything for just I 1 to up to C of logarithm. And then for a given I would like, I first take ID V I as a pair, ID V I minus 1 and ID jump V I minus 1 of I minus 1. So this means I just divide the path into two parts of equal length, and I have such identifiers. I assume that I have assigned them for smaller values of I. And then what I actually do is I just have to renumber such pairs starting from 0. So then renumber pairs starting from 0. So this is a single slide starting from 0. So this is first. I do it just for all of V. I do this part, and then I renumber the pairs starting from 0. So this way, and like when renumbering the pairs, I have the identifiers of words of the length to the power of I are all consistent. So if the paths have equal identifiers, then the words are equal. If not, then not. You can either use sorting on such an array of pairs, just simple sort. You can try backend sort if you would like, not like complicated code, whatever you choose. And afterwards, and during the same process, during the same algorithm, I do exactly the same on the sequence of bits. So I do perform this in parallel both on the graph and starting on the sequence of bits that I am considering this very moment. So I do the same the whole algorithm is performed on this graph that's given here and on a graph like V1, V2, up to Vn. So I take both for this graph and for this graph, and I do it in parallel so that the identifiers in both graphs are consistent. So if here is the same path, then here is the same path. And now if I have computed both such arrays, then checking if this pattern occurs at a given position is actually quite simple. I need to find, so assume that this is just here the graph that we have, example graph that we have here. And what I would like to do is I have to check if this path corresponds to this sequence of bits. So I take the largest power of 2. So I take 2 to the power of floor of logarithm of f. And I would like to know if these two identifiers match the corresponding identifiers here. If this is the same as this, and this one is the same as this one, then we have just a match. And what do I do for this? Well, not that both of these identifiers have already been processed. I just need to, first of all, take if this identifier is equal to this one, so I just check the identifiers equal. Then I jump by this number of positions, both from here and from here, and I check the second pair of identifiers, which I already stored. And that's all. I just check it for all. For each node here, I just check if such two identifiers are equal or not. This is the whole algorithm, actually.
cycles. Like what is the best path because this way and then round and round and round.
Perfect. We don't care. Like, no, just. As we see, we actually, well, first of all, we just drew such a graph and showed how its structure looks like. And afterwards, we just ignored the structure of the graph, as you might see. And we just didn't care, actually, that it looks like that. We just cared that from each node, there's exactly one outgoing edge. This is what is important. So there's no choice, actually here. If there were some choice, then the algorithm would be way more complicated. So I just wanted to point out to you that this technique is like a very neat one, and it's very good to like know about the existence of such doubling technique. The same stuff can be used for computing lowest common ancestors of nodes and so on. So it's also some doubling technique. And one thing that one should take into consideration in that particular task was the memory limit. Because here the array is like n times log n, and it might somehow exceed the memory limit. But note that we always just store one row of this array, like the two consecutive rows. We just store idvi and idvi minus 1. We don't care about the previous ones during the computation. So we can have like memory we can get from n log n to linear if we just don't care about storing previous arrays. And time complexity is either n log n if you use bucket sort for sorting these pairs, or you have n log square n if you just sort. And both such solutions should have passed. So there are way more complicated techniques to solve this problem. You can even try to do it in linear time with some KMP modified stuff. It's very difficult, and you can do it manually. Okay, so this was just the one thing that I wanted to come back to the previous problem set. Yes?
Can you talk about the other problem, Python root base?
So you'd like to hear a few words about Python root base? Okay, this is a very nice question because actually that problem is very similar to this one. Yes, you don't see it at the very end. Okay, so let's just jump to the Python root base problem. It doesn't look like, but you can solve it with a very similar technique. But it's totally useful. So the Python root base, maybe I'll just in a few words say what was the problem about, because here the problem statement is much longer. And then we can get to today's session. Now there is one trick in this problem that's totally out of the box. Apart from that, it's very similar to that. So we have a number of crossings and a number of segments which are either horizontal or vertical, and each segment joins some pair of crossings and doesn't contain any crossings in its middle. So we have at most 100,000 crossings, and at most these are road segments. And it is important that all horizontal or vertical. And one of the crossings has number 1, and one has number n, and they are located like this. So this number n is located down and to the left from 1. And all the other crossings are located somewhere here. And we can only travel, like using the road segments, we can only travel either left, either right, or down. So this is how we can travel. And we have a nice assumption that we will be using, that each of these crossings can be, so from 1 you can get to any of these crossings, and from any of these crossings you can get to n. So all the crossings are just like this possible to get. And the question is, we are given a pair of crossings and a number of queries. Each of them has the form just given a pair of crossings, so we have K up to 300,000 queries. And each query is of the form, we are given two points, and we want to find out whether or not we can use the road segments that exist to get from one of them to the other. So here, for instance, there could exist such a road segment. However, on the other hand, if the crossings look like that, then of course you cannot get, just going down and right, you can get from one of them to the other. But apart from that, there could be a chance that, for instance, from here you cannot get here because there are just no road segments leading from here. So we have a number of queries and we want to answer all of that. And then what the solution is the following. We have a pair of points. And we draw a rectangle with one of the points in there. So first of all, like if the case looks like that, so we have one of the points is to the right and to the up from the other, then we can always say no, and we don't care about such points. So we only care about pairs of points, so that the other is to the right and down from the first one. So if the answer is not obviously no, then we draw a rectangle. So this is the point A in the query, and this is point B. And we consider, now magic comes, we consider two paths. We know that from A, one can get to N. There is a path from A to N. So we choose two particular paths. The first one will be the down path. The down path, I start from A. Whenever I can go down, I go down. When I cannot go down, I go right. Just prefer down. Actually, however I go from A, if I always go this way, I will eventually get to N because from each crossing I can get to N. So wherever I get in the graph, I can get to N. Similarly, I define the right path, which is preferred right. So I have these two paths. And I would like to know how are these two paths located in this rectangle. In particular, if I have these two paths, I'd like to know where do these paths exit the rectangle. Not that when such a path exits the rectangle. So assume that this is this down path. This, and now it exits the rectangle. When it exits the rectangle, you cannot go back to the rectangle. On the other hand, the right path looks similar. Maybe I can go here, maybe here, maybe here, maybe here. Maybe I can go along the border, and then I exit that rectangle. So this is the right path. And this is the down. So now, the question is whether from the structure of these two paths, I can read whether or not there exists a path from A to B. And the answer is yes, I can do it. If the down path exits the rectangle somewhere here, like in this region, and the right path exits the rectangle somewhere here, then the answer is positive, and otherwise the answer is negative. And why is that? Do we see that? I see that some people are already nodding their heads. So,
Wait, what?
yeah.
What if the only two perfect paths are those? Like the one marked in blue and the one marked in green? Isn't that all?
No. Why not? One particular thing. I claim that if these two paths look like that, then there is a path from node 1. I don't know. Somehow disappeared. So then I claim that there's a path from A to B. Why is that? I know that you can get from 1 to B because it is guaranteed in the problem statement. And if I can get from 1 to B, I can get either here or here. I have to cross one of these two paths. And when I cross it, this means that, so how about drawing red? So there is a way to get from here to here. And when I cross it, I just have the path. This gives me the path from A to B. On the other hand, if the two paths just avoid B, then there is no way of getting from A to B, because if, for instance, if both of these paths would exit on this side, then actually, and this was the down path, so you cannot get like more down than on the down path. Okay, so this is the basic observation. Well, it's not simple, but the basic one, the one without it is hard to solve. And now the only thing I need to know is for each of those paths whether or not it exits the rectangle here or not. So I cannot really do it this slowly. Yeah? I have to do it fast. I have almost a million of queries. So what do? I just use the technique from the bits generator program. I find the down paths using the path by one edge, by two edges, 4 edges, 8 edges, and so on. So from each node, I get down from a node and I, which is just in the bits generator, and right from a node and I. Yes, so if I go to the power of I steps, to the power of I road segments, from V on the down path where I get, and from V on the right path where I get. And if I have this doubling stuff that I can just try to binary search this position where the path first exits the rectangle and binary search this position. Yes, but this problem I consider way more tricky than the previous one. And it's quite interesting that, for instance, when we had the same contest in Poland, there were two teams who managed to solve this problem, but no team who solved bridge generator. Why is that? They prefer the more difficult one.
Did they use this technique or
Something similar, like similar observations. Not this very observation, because like this observation is just very polished for you. Yeah? I just give you that the simplest way to show you the observation. But well, you don't always think it like that, but they did something similar, in a sense. But yeah, but still it was considered much more difficult. Okay, so from that very contest there was also one problem that we didn't discuss yet. The problem about ends. And as for the problem about ends, I don't think it makes, because it's a very tricky problem, and it's not a typical one. It's just more because here in the ends problem you cannot really afford to store all the input in the memory, so you just have to be very low on memory. But it's not actually an ICPC task. We don't have such tasks at the ACM ICPC. So I think that the best way to do, because this problem about ends is by accident described in this book that I promised to award to the 5 teams. So maybe we can just start by awarding this book to the 5 top teams from yesterday, and then these teams can read it and tell all the other guys how to solve the problem about the ends. Because it's a very short description here. So maybe I can just, I'll just recall the results from yesterday. So the 5 top teams. So the team number, and maybe then if I can just meet those guys, I can know which teams are there, because I don't know all of you yet so well. And so the first team was the team from UFPE, which was fun to win. We have this team here. So maybe we can just, they solved 4 problems, so it's been a nice time, congratulations. The team from the 4th place is Lord Stefan team. This is an IME, USB, ASA, however you call it, also for problems, so congratulations. And then there are 5 problems. The team, it is not a team from Senora Margarita, I guess, but Senora, I have so this is a team from ICMC. Yes, and on the other hand, maybe one of you lost your identifiers. Carlos as well. Yes, so okay, so maybe I can award both the identifiers. There was on the 2nd place. There is this team from Unicamp. 5 problems. Congratulations, Oscar Colas. And the winners of yesterday's contest with an outstanding performance is the team of Ita jQuery, Bull jQuery Char, however. Yeah, so the first problem discussed in this book is just the problem of n, so then you can just everyone else how to solve it. And we can try to proceed to yesterday's contest so that we like make some stuff. We are able to tell a few words about it. So almost all the problems were solved yesterday. There was just one problem that wasn't solved, and actually it was not meant to be solved. So the problem of gates, I just put a very hard problem. Just if someone gets 9, then he'll get stuck on this. So it wasn't supposed to be doable. So it wasn't trying to be doable. So you don't have to bother about that one. But from time to time you have such a problem at some competitions where you don't find it doable. And maybe we can now proceed to several of these problems. And today's theme for the second part of the class, we usually have some theme, will be based on two problems from yesterday. One is about mosaicism and one is about programming content. So I would like to then say a few words about some exponential solutions to problems. So you either have NP complete problems or similar stuff and you want to solve them, however, it is really important how fast you solve them. And there are plenty of such problems at ICPC finals, so I would like just to say a few words about these in the second part. But when we start with the simpler ones, simpler problems, we won't be considering the problem of strips. It's yet another 3D problem with 3D solution. Where is the graphic? Okay, so almost most of the teams managed to solve this problem. We have discussed quite a lot of 3D stuff yesterday, so we can just omit this one for the moment. And then there was this task that I really like, the task about motorways. One more thing, because you sent me 3 emails yesterday with some errors in this problem statements. Unfortunately, you are all right. I'm not sure how that happens because what I give you here are the official translations. And for instance, if I compare the Polish version and the English version, sometimes this number 8 to 9 just changed in the translation. I don't know how it happens. So actually, I have to apologize. I never read the English statements. I just read the Polish ones normally. So I didn't really check this stuff. So well, these errors weren't as bad as one could get. But so if you have any doubts during the competition, like you don't get something and so on, just don't hesitate to ask me. So just send me an email. I'm answering these emails for most of the content. So if anything is wrong, then please let me know. And of course, we will correct those in mail and in the official translations. So there was this task about motorways, which is actually quite funny, because the solution to this problem is extremely simple, but you just have to be brave enough to code it. Decide to code it. So you have a graph. So the task about motorways it won't be long. We have a graph that is directed or whatever, it might be directed, it might not be directed. We have some source node and some end node, and we want to find which is the cheapest path from S to T and back. Again, whatever, from wherever to wherever, actually from one node to another. And what we want to know is, so we want to have the cheapest path, and the length of the paths differ in time. So for each of those of the edges of the path, we know that whether this edge in every second increases its length increases by something, or is it 0, so it's constant, or whether it decreases by something. Yes, so for each edge, we have a difference. D could be positive, could be negative, so that in every second, every unit of time, every day, whatever, it changes just by the weight, the length of the edge changes by T. And I want to know the shortest path, whatever, from S to T, let's say, don't consider this one, this is similar. So I want to know the shortest path from S to T at any point of time. So I want to find this very day when the shortest path with these varying lengths is the smallest. And the answer is a bit surprising. You take the first day, you take the last day, you take the shortest path on both of these 2 days, and you take the and that's all. So actually the solution is and for the shortest path you use Dijkstra's algorithm. So So the only thing that you have to prove somehow is to show that that this is enough. Yeah? The sum is to take the first and the last day. And for this, the argument is also quite easy. However, for this argument, you have to somehow get the right idea. So assume that I have a path from S to G, and let this path, this very path, be the best path ever. So the shortest path has the best day when it is considered. So this is on some day X, and this path happens in day X, and this is just the best shortest path that you can get. So this is the result. Okay, so consider the sum of differences, like these differences on this path. If it is positive, then this means that one day earlier, the length of this path was even smaller. You cannot have that because this is the best path. If it is negative, then the length of this path would be, so if the sum of differences on this path is positive, then this path has to have happened in the first day of the process, because then otherwise you could get one day before, and the sum of differences would decrease. Similarly, if the sum of lengths on this path, sum of differences is negative, then either it is the last day, or we have a contradiction because on the next day the length of the path will go on. And the third case is that the sum of differences is 0, and this means that this path is constant on every day, so I can pick the first day or the last day or whatever. So if I consider the best shortest path, I know that this very path will have no greater length either on the first or on the last day. So I just take the first or the last day. And on the other hand, you don't have to try to prove it. If you have the right intuition, just code and get accepted. But it's not easy. Well, when we had this problem at some Polish contest, people wrote some binary search, ternary search, whatever. So because it's not that simple to get. Yeah, but if you see that here we have a linear function and you want to know where is the minimum of a linear function, then you know that no binary search for that. Okay, so this is one task. That's all about this one. There was also another quite tricky, quite rather neat problem about double row. However, this is again a problem about we have some. I'm not sure if I'm really willing to consider this one. Maybe just a few words, and if you want more, we can get into details. Or maybe we can do it just fast. So we have this two rows of people, and we can exchange a pair of elements, and any pair of corresponding elements in these two rows. And our goal is to have these rows aligned in this way that none of the rows contains two repeating elements, any repeating elements. And we know that we can do it, and we want to do it in the minimal possible number of steps. So the minimal possible number of pair swapping. And since we know we can do it, this is a problem that from this setting we have to have a graph interpretation of that. So as in the bits generator, which is still here, we have to go from some pseudocode to a particular graph. Here also we will get to a particular graph. First observation. Each value can appear in these two sequences, and the length of these two sequences like 5, whatever. And each value can appear in these two sequences at most twice. If it appears 3 times, then however we swap, in one of these two rows there will be this value at least once, so we don't care. So each value appears at most twice, and consider the two, if it appears twice, maybe this was this nasty case. So if it appears twice in the same pair, then we just leave it, or we just don't consider this pair, we don't care about it. On the other hand, if it appears twice somewhere else, so if a value, the second appearance is here, then what we do? We create a graph. So here is let me number the positions from 1 to n, and then these two positions so the two positions where the same value appears are connected with an edge. here there will be an edge from node 3 to the node corresponding to this one. So I will draw edges whenever there is the same value at two different positions. And this edge is labeled either by 0 or by 1. It is labeled by 0 if these two occurrences are in different rows. So 0 is in this case. However, for instance, if I consider this one, and then I see that this one is also at this position, we know that an edge from here to here of labeled with 1, which means that they are in the same row. So 1 means we have to do something. We don't like just this one. And we create such a graph in which the edges join the vertices like that. And again, this is a very special type of graph. You see that we kind of like important problems about special kinds of graphs. And this special kind of graph is that each node can have at most 2 edges outgoing from it. Because like one value in a second. So this graph is either a collection of cycles or paths. This is how the graph looks like. And in each cycle you have a number of ones and a number of zeros. Zeros that don't really matter too much. So ones mean that you cannot really, that you have to make some swap. And how does a swap look like? A swap works like this, that if we have 3 adjacent nodes on the path or on the cycle, we can swap. So swapping a pair means like negating the 2 bits that are adjacent to this node where we do the swap. So after the swap here, one will get 0, 1. And we want to know this minimal number of swaps. So what happens here? First of all, note that in each of those connected components, if the number of ones is odd, then we cannot get, using these swaps, you cannot get to all zeros, because we want to get to all the zeros. So this is one condition. If the number of ones is odd, then we cannot do it. And if the number of ones, but we have an assumption that we can do it. So we know that the number of ones in each of these is even. So what we actually do is that we have to match. How can the ones disappear? If I make this operation on a pair of 1 and 0, then this just moves the 1. And if I make it on 2 zeros, I'm crazy, because I'm creating 2 ones. And if I make it on 2 ones, then they disappear. So I either move a 1 here or there, or I destroy a pair of ones. And I know which pairs of ones will actually be corresponding to each other. I mean, if you have a line like this, maybe I have two elements, then I know that this pair of ones has to annihilate with each other and this pair of ones. Similarly here. So here also has to be a 1 so that the answer is positive. And on a cycle you don't know. You can either have it like this pair of ones can annihilate, like one moving to the other and then annihilate, or you could have like that. So on a cycle you can either have a matching like these ones or these ones, and then you take just the minimum out of these. So this is the It's basically more or less everything I wanted to say about this task. There's not to get into too much detail about this. And now the next problem that was very popular was the problem about journey. So the problem about journey is one of these three problems, which are actually something that was exponential here, but it is of a completely different nature. The problem about journey is just about combining two known techniques. If you know those techniques, you can combine them. If you don't know, there's a problem. It's much harder to solve them without these two techniques combined. And maybe I'll just, again, just tell you what are the techniques and how you combine them, and if you have any, if you don't have some idea about any of these techniques. Sure. If you don't have any idea, then you have to just a bit more read about any of these techniques. So we have a graph because everything is small here, so we have at most 20 nodes, and we have at most 7 special nodes. And I want to know the number of paths of length d, not of length n as the third paragraph of the problem statement said, but of length d, which is at most 10 to the power of 9, so this is the length. These are special lengths. These are special nodes. I want to know the number of paths starting in the node 1 and passing at some point through each of the special nodes. So I want to start in one path through each special, and have length z. And since the number of such paths can be very large, you can write it modulo 3. Okay, so the two techniques are, first of all, if I want to know how many paths in the graph are there of length d, what I will do fast matrix exponentiation. So I create a matrix that has an adjacency matrix of the graph. So there's a 1 on an edge in the corresponding row and column if the corresponding nodes are connected, and I take it to d to the power of d. Of course, I take everything modulo. This is something that I have to take modulo 10 to the -9. And here, and the corresponding element of the matrix is how in the past are there. So this was trick number 1, and trick number 2 is like how to cope with these special nodes. And the second trick will be inclusion-exclusion principle. So we introduce the set. So we have all, meaning the number of all paths from one of them d. And we introduce the set AI, which is the number of paths not visiting from the nodes not visiting the node I. And what I want to know is what is the cardinality of the set when I take the set all and I subtract the sum of the sets from A1 to AK. Because I want to take all the paths coming through at least one of those, so I remove the guys that are not in so I have to remove all of those paths from the paths all. And how do I find this? So this is the inclusion-exclusion principle. Inclusion-exclusion. So I take the size of all, I subtract the sum of sizes AI, then I have to add the sum of sizes AI the common part of intersection of AI and AG minus something and so on. So here is minus the sum of AI, common part AJ, common part AK, and so on, for all of such combinations. And we have to know that computing any of these particular ones, for instance, such one, the number of paths that avoid 1 and avoid I and avoid J, I just remove the two nodes from the graph and I count the number and then remove them. They are here. And that's all. So I remove them. So in each of those components, I just remove the corresponding nodes and I exponentiate the matrix and I have one. Here I have 2 to the power of k such components for which I have to do. So 2 to the power of k times I do fast matrix exponentiation. So the time of matrix multiplication simple one is n to the power of 3 and times log d for matrix exponentiation. So this was a combination of 2 tricks that one needs to know to solve this task. And that's all for this program. There are, I guess, around two other problems that I would like to say a few words before we get to the mosaicism and the problem about programming contests. So there's a problem about island. Just a few words about island, because we've kind of had quite a lot of geometry here at this camp that I won't be getting into too many details. However, I tried to give you, I selected this problem set yesterday. It was just selected by hand, so no one ever tried this particular contest. I just selected problems that I wanted to propose. The problems that I actually tried to select were the problems that I would see like in the level of medium, somewhere a bit below medium, somewhere above medium of the ACM-ICPC world time. So this is most of the problems, like not taking into consideration the first 3 or 4, were just medium or something around medium that I would see at the world finals. And this problem about island studied by one of the guys who is now one of the judges at the CMI-CPC, is from Poland. So that's why from time to time I try to select problems which are like created by people who then create problems by the CMI-CPC, so that you can get some idea of how such problems look like. So the problem about island is we have an island which is a convex polygon. We have a starting node n and final node 1. But we can also, it's much easier to consider this problem as starting from 1 and ending in n. You can get a much easier idea of what the problem is about. And for a number of such lines, so a number of such diagonals, we know that they are forbidden. They are blocked. You cannot use them. So we have, so we have n at most 10 to the power of something, 5 nodes, and at most 10 to the power of 6 forbidden edges, forbidden diagonals. And I want to get from 1 to n using segments of diagonals. And what I can do, of course, I can close these forbidden diagonals, but I cannot go along them. So first, if this is not forbidden, then I can go from here to here. For instance, then I can go from here to here. This is one way of getting from 1 to n. So I want to find the shortest path from 1 to n that always goes around diagonals. You could also go around edges, but assume that this one is also blocked, so that, well, if this edge from 1 to n is not blocked, then certainly the shortest path will be just from 1 to n. So this is one special case that we can consider, and from now on, assume that we are only going around these diagonals. And we can, so the number of forbidden diagonals is not that large, but the number of non-forbidden diagonals is quite large, because all the other ones are not forbidden. And first of all, the first idea is to try to limit the number of useful edges. Like the useful ones are the non-forbidden diagonals that you really have some idea why you try to use them. And to limit the number of useful diagonals. So again, I got it wrong. So this is 1, this is 10. So assume that I have node 2, and assume that both of these diagonals are not forbidden. So this is some I, this is I plus 1. Or maybe I plus j. So this is so what I know that this one is totally useless. Why is that? If it has a path from 1 to n that would go somewhere here, then use a part of this one and then go somewhere here, then this path would have to cross this one at 2 points, at least 2 points. Maybe it's like going crazy, but it's pointless. So then, like, making a shortcut here makes the track short. So from each of those nodes here, I only care about the lowest diagonal leading from this guy, because all the other diagonals are that useless. So I have the most and useful diagonal. And from here, it's all. And now we get actually. So what I have here is I can again go to the language of crossing semiplanes. So each of those useful diagonals, if I have a useful diagonal, then I know that this creates me such a semiplane. Then if I have another useful diagonal, I have another semiplane and so on. And from 1 to n, when I get from 1 to n, this path from 1 to n is of course the shortest one. I don't want to exit this area. So just I want to find the shortest path that is convex and just goes from 1 to n. So this is the common part, the intersection of all these half planes. You take all these half planes and you take the intersection, and the boundary of this intersection is the shortest path that you can actually find here. So I want to have again, I have n half planes, then I want to know what is the their intersections. This is a problem that we try to consider on Monday. Actually, the solution is like that you have to, like, they are all sorted from the, like, by the starting positions, and you store every one of them in a stack, and then you remove several ones of them from the stack. So when you add a new half plane, so you consider the half planes in this order, and you do something similar to Graham's algorithm of convex hull. When you meet a half plane, you just see where it crosses the other half planes that were already there, and just remove a number of them from the stack if it crosses them this way that they are big connections. So this is from here now, it's like the less pleasant geometric part to code, but you have to know how to code such stuff. So this is basically partially the trick that we mentioned yesterday, on Monday. Okay. We're going quite fast today. Maybe the problems are, it really depends on the type of the problems, how fast can you get with the solution description. Maybe let's also say a few words about this problem of neighbors. It wasn't that popular here. Yeah, just one team managed to solve this problem. And maybe this will be the last one before we get to the two major ones. So the problem of neighbors was maybe not that complicated to like figure out the solution, but coding the solution might have been a bit exhausting. It also depends on how you want to do it. So we have a very large grid, very large. WH are at almost 1 billion. And we have quite a large number of points in this grid somewhere. And what I'm interested in points. So for each other point from these points, so the number of remaining points is huge. So each of the remaining points, I want to know how many neighbors it has, where the neighbor is like the point to the up, to the left, to the right, and to the bottom. We have a neighbor if one of these n given points is located just to the left of it, to the up, to the right, and to the bottom. So the number of neighbors, actually from a point may have between 0 and 4 neighbors. 0 if none of these guys, so if in none of these directions there is a neighbor, 1 if there is just in one direction, and 4 if there are 4 in 4 directions. And I want to know how, for each of those, how many points are there with this number of neighbors. With this number of neighbors. And then the fifth one, the most difficult one, will be just from all the other, from the number. So I have 0, 1, 2, 3, 4. These are 5 results. And one of those can be computed as W times H minus N and minus the sum of the others. So we can select the one that we don't like the most and just subtract it from this result. Okay, so it will be easier. So the easiest ones are, so here the difficulty just increases as we get closer to 2. So for instance, how many points have 0 neighbors? So which are those points? These are the points that are located both in a free column, so there are no other points in this column, so there are no up-down neighbors, and in a free row. So I know the number of free columns, I know the number of free rows, it's simple to compute. So I multiply these two and I get the result. So 3 rows times 3 columns. On the other hand, for the value for 4, so how each row, I can consider all the points in this row, and if there are more than one point in such a row, then we can create segments like this. So I know that on the whole segment like this, from the first to the last point, provided that there are more than one of them, any two points that will be located on this segment will have these two neighbors. We'll have this neighbor, and we'll have so we'll have these two neighbors on this like the horizontal ones. And similarly, if I have more than one point in vertical order, then we can say that each point here has two neighbors, like top-down neighbors. So here, what we have a number of horizontal and vertical line segments, and I want to count the number of intersections. So number of intersections of some vertical plus horizontal segments. And this is easy to implement. We have a number of segments, and actually what we do for this, the best way is just a line sweep algorithm. So sweep. So you take so you have the events. The events of the broom are either a vertical segment, either horizontal segment starts, or a horizontal segment ends, or we have a vertical segment. So first of all, because the coordinates here are very large, we'll be storing some kind of a segment tree, a Fenwick tree, whatever you call it, that can just enumerate the number of points in an interval. So first of all, I have to renumber the coordinates of only the points that we are interested in. So the first step one is just renumber the coordinates. The coordinates, so that the coordinates from 1 to n get to from 1 to w get to 1 to n, and from 1 to h they also get from 1 to n. So I renumber the coordinates, and then after I have renumbered the coordinates, we can just do so. When I have an event that the segment started, I put the segment in the so I put this segment in the data structure. When I have the segment ends, I remove the segment from the data structure. And when I encounter a vertical segment, I don't know how many horizontal segments are there, which are at this moment in the broom, and which are from this to this y coordinate. So we have to just have a data structure that enables the operations insert, delete, and count in an interval from A to B. And this is some kind of segment tree, Fenwick tree, whatever tree. So this is how we solve point 4. Okay, so we have 3 remaining ones. Now let's get back to 1. So the number of points which have exactly one neighbor is also it's even simpler to compute that. This is 1 through 4. So what we have, so to have exactly one neighbor, I have a point, so there must be consider the points that have only one horizontal neighbor. So I need to tell you if I have a row and there is a number of points, then actually I'm interested in the points to the right and to the left of the only point here. So all these points here and here have exactly one horizontal neighbor. All these points that are here. You have to choose just the points here, so that here are 3 columns. So any free column here, so at any point that's in an intersection of a free column here, and to the right of the rightmost point of the given endpoints in a given row, corresponds to, so it has exactly one neighbor. So I just iterate for all the rows. I take the leftmost and the rightmost point, and for all the rows where there are actually any points. And for this position, I have to know how many free columns are from here to the right. So I can just store the number of free columns, and or maybe store the number of non-free columns and subtract from all these numbers the number of free columns in this range. So I again have to have some data structure that gives me the result. Give me how many free columns are other from this position to the end. So data structure here, this necessarily is how many free columns from the range from A to N to W, for instance. Yes, or in the range from 1 to A. So here using this data structure, so I multiply like 3 columns. So like the formula here is just we intersect segments with 3 columns. So again, if you are like feeling comfortable about all these simple data structures that you can just solve point 1, so now there are only 2 remaining cases. So maybe let's go to case 3. Case 2 is a bit messy because you can either have it like this, so that you have such 2 neighbors, or you could have it like this, so you have such 2 neighbors. Well, actually, you could also solve case 2, whatever. As for instance, how to solve case 3. For the case 3, it is very similar to case 4, so maybe it's then it is easier to compute how many of these are in case 3. So in case 3, if you have 3 neighbors, then it looks like that. You have 1 segment here, and there is just 1 open segment, so you have this point, and this is like goes to the end, so there's no other point here. So here it all comes down to intersection of horizontal segments with both endpoints in the points that we are given, and vertical segments with 1 point in one of the points that we are given, and the line going just straight bottom until the end of the grid, and there are no points here. So I have again intersection of segments. Of course, of this form, and then on the symmetric form, where you have 1 segment has both endpoints and 1 has just 1 endpoint. And then for the case 2, you can just have, so you don't have to consider case 2 because there are 2 subcases. So you take all, so you take W times H minus N and minus case 1, minus case 0, minus case 1, minus case 3, and minus case 2. And you have to always like remember not to count the points, either not to count the points from these n given points because they are not to be counted, or if you count them in any of these ways, just subtract them during the computation. Okay. So there are quite a number of data structures just running around here. One data structure, other data. You just have to like consider which of these 4 results are. So I'm not really surprised that there are not so many submissions for this problem because, well, conceptually this problem is not so hard, but coding is like a bit of coding. So, but still, such problems also happen. If you don't know how to solve any of the other problems, then solving such a problem would make some sense. And now maybe a few words about this mosaicism problem. And so we will be getting into real stuff. So here, it is not actually an exponential time algorithm, but we use tricks that are used in exponential time, in problems with exponential time algorithms. Somehow lost the rapid list. It is here. So about mosaicism. I apologize for not giving you the figure in color. Unfortunately, we couldn't print it, but if you wanted just to see the figure, you could go to the website. So maybe it is easier because like you have to have a good interpretation of what happens in the problem statement. So I'll explain to you the problem statement in parallel to with the solution actually. So we have a number of fakes. And for each fake, so I will be creating n bipartite graphs of the following form. So for each fake, I do something. There are n fakes, n and most what I do, I create a bipartite graph where this fake has a number of genes. So here are different kinds of genes of this fake. The genes are numbered from 1 to 100,000. Well, this fake contains at most 300 genes. So like genes is always at most 300. So there's a common limit of everything. And on the other hand, we have all the other fakes. The number of fakes is almost 300, so that maybe that's the code. By the capital M, we have just 300, so everything would be less than 300. And I draw a graph so that some pairs of genes are connected with some pairs of fakes. So for instance, there is this gene A, and is connected with fake I. And this means that this fake contains this gene. And what I want to compute is, I want to compute the number of pairs of edges, so that we have an edge from A to I and from B to K, such that they are all different, I guess. Yes, A and B should be different, and yes, I think so. Yes, such that yes, A is different than B, I is different than K, and there are no edges of the form AK and BI. This is what we can actually write. So I'm interested, so I have AI, I have BK, I have an edge here, and so I have to have these two edges, and in the red color I will say these two edges are not here. You cannot have these two edges. You just have these two edges here. And I want to count how many such pairs are there. So I have n kinds of, like at most m kinds of these problems, and each problem has, the graph has size m by m, so it has m squared edges and m dots. And I want to just count all the stuff here. It was not fairly like that simple to create, like to read this stuff from the problem statement, and after you take a look at this for some time, you see. So the question is, so I have, so a single problem of this type, well, first of all, you could just try to solve it in a like brute force way. In a brute force way, you would select one edge here, then another edge. So since there are m nodes and m squared edges, you can take a pair of edges. So there are m to the power of 4 pairs of edges. And just check if this pair of edges is good or not, so if these two edges are here or not. So this would give, in total, because we have m such bipartite graphs to consider, m to the power of 5 to have this number of such configuration, so this complexity, and this is way too much for m equals 300, so this is too small. So actually, to get a bit faster, it's not even sure whether m to the 4th power is enough, and it is not enough. Well, it should not be enough. Maybe you have to like do some improvements to get to n to the 4th power. But we will try to design an algorithm that works in n to the 4th power, and then say how do you actually, what do you perform? And here I want to. It's like just. It's just sufficient to note that all the results can be computed from some simpler stuff. Simpler stuff is, we have to compute NA is, for a given gene A, how many edges are there going, leaving A? How many edges adjacent to A? So gene A. This is one thing that we have to compute. The other thing that we have to compute is NAV. How many genes are there that are connected with an edge both with, how many fakes are there that are connected with an edge both with gene A and with gene B? So, how many fakes I such that there exist edges AI and BI? So So here I just, for the gene A, I want to know how many edges are there, and here I have two genes A and B, and I want to know the number of such configurations.
I didn't read the problem statement, but didn't you say that if you had a relation to the AI, you can't have a relation to the array?
You cannot have it in the result. So you want to know, so this is not an assumption on how the graph looks like, but this is an assumption of what is the result. So the result is I want to count how many configurations are there, such that there is an edge from A to I, from B to A, and there are these two edges not here. So this is possible, however, we want to avoid it. So that's why we will be actually subtracting this stuff from our result. And now the question is how to compute. So I would like to compute using these two parameters. I would like to compute the result for A and B. So let's call this stuff, this whole condition, result of A and B. So roughly how does it work? I'm not sure if I will just restore the formula correctly, but more or less correctly, so that you get the idea how to get this formula. Actually, by trying to get such a formula, you can actually figure out that you need these two parameters to just go for it. So first of all, what do we have? So I want to compare with the result of A and B for any two different pair of genes. So first of all, I can take, so we call it what I want to have. I want to have A with something, B with something, okay, and these two not exist. So first of all, I could multiply NA by NB. This is very rough. I just take all the edges from A and all the edges from B and multiply the stuff. So I have counted some stuff way too many times. So what I have to do? First of all, what is wrong here? If I take any edge from A and any edge from B. One thing that is wrong is that I can have I equal to K. So this is just all. And I have to subtract the cases where I have selected two times like the edge that goes to the same point. So I have to just subtract NAB, which are the cases where I equals K. So now I know that I only have, after subtracting this, I only have such configurations. But now I need to avoid configurations when this edge exists or this edge exists. Like I don't want these edges to exist. So for instance, if this edge exists from B to I, then how many configurations of this form are there? Well, then there is NAB is the number of such configurations times the number of edges I'm going from B except for this one. So times NB minus 1. I don't want to count, so from these configurations I need to, so I replace the configuration by like this and like this. So this is a wrong configuration. So here I select I and here I select K. Similarly, we have to subtract NAB times NA minus 1. These are symmetric configurations where we have those two going here and we have this additional edge. And we have to care right now at the very end that we have considered some stuff twice. So if we have such a case, and if we have all these edges, then we counted this configuration once for this stuff, and the second time for this one. Okay, so this red one was in this component, and this black one was in this component. So what I need to do is I need to add, because I have subtracted too much, the number of such configurations, which is just sorry, no, I want to go to black again. So I need to add the number of such configurations. It depends actually. We have to like care if we really care which is the first node and which is the second, which is the first, second, which is the second. Here I guess that we care, so we have NAB times NAB minus 1 and that's all. It could have been divided by 2, but maybe here it doesn't have.
Sorry, I don't get to see the difference between the three terms in the middle, like what each of them stands for.
Okay, so this one stands for that A and B are just related to the same thing.
Okay.
So from now on, we can assume that, so from here, I assume that I is not equal to A. So these two fakes, I and A are different. So now, so now I have only such configurations, and I want to make sure that none of these two edges exists. So I subtract from the number of all configurations, the configurations where none of these exists actually. So, because this is all for now. So when it exists, so this edge, if this edge exists, then here I have such a triangle which is in NAB, and here I have an edge which is in NB. And I multiply the number of times this stuff happens by the number of times this stuff happens, but I subtract 1 because like I don't want to consider this edge twice. Similarly, like the symmetry case is here, and here I just have to add this stuff because I have subtracted too much. Such configurations and such configurations, like this kind of configurations and this kind of configurations, like these N-shaped configurations repeat, actually. So I have to just add the stuff that I have subtracted too much. So I think this is the easiest way to look at this problem. But I've seen several different solutions. Some people just like solving this problem by just writing like a sum of sums of sums of sums and then just transforming these sums. But I'm not really into such solutions. Maybe one way to go. And after we have this, if we could guess that all these parameters are actually sufficient, then what we can do is we just have to count for each thing. We have to count each NA and each NAB. What is this value? So our basic problem is count NAB and NB. And NB. And counting NA is trivial. You just count the number of edges, which are adjacent to a G. NA is just trivial. And the more interesting part is NAB. I want to know for each pair of fakes, there are m square pairs of fakes. I just consider all the for each pair of genes, I consider all the fakes. So genes are to the bottom and the fakes are to the up. So each pair of genes, not genes. I consider the fake, and I just check if these edges are here. And since we perform this stuff n times, this is the time complexity of the solution. And you are happy you code it, and hopefully you get the limit exceeded for that. It's a bit too slow. This should have TLE, the limit exceeded. But we are not very far from getting accepted if you have written it this way, because we have to use a trick. Because actually, I wouldn't suspect it to be present at the World Finals, but it seems that at least one of our teams used this trick at the last World Finals. And there was this problem about inception or something like that. How was it? Inception, yes? Infiltration, whatever, okay, in whatever. So there was this problem about infiltration where you could actually try to use this trick. And the trick was that you have, so what we actually have here is I want to find, so I have two pairs of genes, and I have a pair of genes. I have a pair of genes, and I want to know what is the number of common neighbors. And for this I can divide the complexity by the number of, by the size of the integer type, right? By the number of bits in an integer type. So the problem is that I have this gene A, I have this gene B, and I want to know what is the number of such common pairs of edges. So then for the gene A, I can store a table with bits that gives me which phase are there to which there is an edge from A. So I have a table like Boolean bit mask. Okay, so maybe just a bit mask, which gives me bit mask just B. TA, which gives me TA of y of I, is there an edge from A to I. Similarly, I have bit mask TB, which says, is there an edge from B to I? And what I want to compute is I want to take the bit mask TA and compute where these two bit masks, how many positions. So I want to find the count of the number of positions where these two bit masks actually overlap. So where they have once, so I manage both in A and in B. And for this, since you already, I think, recall the trick from the problem in the world finals. So the trick is that you can, for instance, divide both of these bit masks into parts of length 32. So I have TA, I divide it into parts of length 32, like 32 bits. The same for TB. 32, and so on. Each of them can be stored in a single integer. One in here, one in here, one in here. And then I just go through all of these integers, and I want to know how many bits are there in the end of these two, after end operation of these two integers. And to find this, what we can do is that we can use for instance, the built-in pop count operation that given an integer, it gives the number of 1 bit in the integer. So for each pair of these integers, I use the AND operation, and then from these AND operations, I just use built-in pop count to find how many of these bits are what and how many pairs. Well, this is C++ specific, but there are also other ways of finding how many bits are there that are faster than just counting the number of bits. However, I hope that being C++ specific is just harmful for at most one team here, so maybe we support. You somehow recall this number, almost, yes? Some yes. Who recalls some stuff? Oh, so not that many. What we call? Yes, I will build the pop count on this trick. Yeah, so some people recall this trick. Yeah, so this is in like GCC compilers. We have to have a GCC compiler to have this built-in pop count function that just does it. So we cut this into parts and then just, and so this reduces the time complexity from m to the 4th power to m to the 4th power divided by b, where b is the number of bits that we can actually put in an integer type. So here b is 32. So dividing the time complexity by more or less 32, we get a solution that like passes the test without any comparison. Yes?
Minus n cubed and what like
N cubed? Wow, you can solve this in N cubed.
It was I calculated wrong. And I thought it was n cubed.
Okay, so maybe we can talk like after this discussion, because we don't know how to solve it in N cubed. So.
No, but I mean, can't you just sort all the names in its base and those numbers
And then you have N cubed.
Yeah?
Okay, we have to talk after the discussion. So this was the model solution. Maybe actually this problem sounds like computational biology, and there was a guy from working on computational biology who gave us this problem. So actually, like the problem was from somewhere. Like we didn't really invent it. So this stuff was not invented just off the top of our head. Okay, so this was a problem about mosaicism, and the other one that I was willing to discuss. Well, here the most important trick, I guess, for me was this one, but actually it is also quite interesting that you can. Well, many of these problems are somewhat about enumeration of things, yes? If I want to enumerate the number of paths in a graph, I can use some matrix multiplication. If I want to enumerate the number of special points, like in the neighbor's problem, I have to have some intersection of something. If I want to enumerate the number of such options, I have to have a smaller set that I can enumerate, so an A's and B's and an AB's, and then just from this extract this stuff. So there are quite many problems about enumeration, and now comes the problem that I think was, well, you were most interested in this problem. Actually, I got a few questions after the contest. Well, you gave us an incomplete problem. How is that? How could you? And people tried to have brute force algorithm for that. And, well, you have to have the right brute force to solve the problem. So I think this is the most important problem from this contest. So, and it was about the programming contest. So I hope that most of you recall the story. The story is that we have, so well, there are two parts in the problem. First of all, you have to extract from the story some real problem, and then from this real problem get to solve this real problem. So we have at most 400, which is what? And is at most 400 tasks in a competition individual. We have K, that is at most, so we have K contestants. We have M topics. And I have the setting, and I want to choose I want to choose n tasks out of several different topics, so that the contestant 1 wants to win and wants to select the problems of these topics. And for each of the contestants and for each of the topics, so we have a K times M matrix, which says if this for this contestant and this topic, how good is this contestant in this topic? So integers, how good is the contestant in the topic, given topic. And I can, how the score is computed. The score is computed so that if I have a problem with from a given topic and with a given hardness coefficient, then all the guys who have for whom from this coefficient on the matrix is at least as large as the hardness coefficient solve the problem, and the number of points they score is by how much they have. So by what is the margin? By how large they meet. So if I have a problem from topic J, which has hardness H, then all the people who solve it are all the people solve this matrix. I don't know, M, whatever. So the people with M, I, J, at most H solve it, and for this they get an additional score of Mij minus H. This is the score they get for solving this problem. And first of all, I want to do it so I can write either on the number of tasks. So the first criterion is the number of tasks solved, and the second criterion is the total additional score that I have. It's a bit complicated, unfortunately, the problem statement. But this, and I want to check if I can win. And there is this, I haven't just written one small condition from a program statement, which is absolutely crucial for this problem, which says that K times M is at most 400. It is totally crucial. And many of you have noticed that this reduces actually to a problem what we call a set cover problem. What happens here? How is so we can show that actually this additional score stuff is totally irrelevant. We don't have to care about it. And I just need to find problems so that select a set of problems so that the contestant number 1 will win. So it will one contestant will solve as many, more problems than anyone else. If there exists such a selection of tasks, then that is okay, and it's not that you cannot really select the tasks in the proper way. And first of all, we have to make one observation that choosing a task that is not actually solved by contestant 1 is pointless, because we give points to some other guy and we don't give points to contestant 1. So we only give tasks, not only give tasks that contestant 1 can solve. Actually, then what we have to do, we would like to select n tasks, preferably of different topics. So at most n tasks of different topics. And if we select some at most n tasks of different topics, and for each of those tasks, the difficulty level will be just the value Mij, so M1j. So this will be just the value how good is contestant 1 in this type of task. So the hardness will always be M1j, which means that we just don't want to lose. We don't want to give any. If it is harder than contestant 1, we won't solve it, so it's pointless. If it is easier, then maybe someone else can solve it. Like some other people can solve it, so it's also pointless. So I want to choose at most 10 tasks of different topics of this exactly this hardness, so that each other contestant cannot solve at least one of those tasks. So that every other contestant cannot solve at least one of those tasks. This is what I want to do. And if I can find such a subset of n tasks, then I succeed, because everyone else loses to contestant 1. And on the other hand, if I cannot find such a subset of tasks, what does it mean? It means that contestant 1 on this particular subset of tasks, so for every subset of tasks, of n tasks, there at least exists a contestant that can solve all the tasks as good as contestant 1. Maybe the contestant is even better, like has a better coefficient of how good he is on any particular topic. So actually, if such a combination of tasks doesn't exist, it means that for every combination of tasks, some other contestant dominates contestant 1. So he's better on everything in this set. So we cannot beat this guy. Regardless, not considering the additional score, whatever. We just cannot beat this guy. So if this exists, then so we have two things to show. So this is the combinatorial observation. So if this exists, then we have the result. We are done. And if it doesn't exist, then it means that in every selection of tasks, some contestant dominates contestant 1. So this proves that additional scores don't matter. So what we have here is what is the set cover problem right now. So for each type of tasks, we have a set. So set Sj for j from 1 to m, or topic from 1 to m, is the set of contestants which are at least as good in topic j than contestant 1. Contestants as at least as good in topic j as contestant 1. And what we want to choose, we want to select at most n of these sets that cover all the whole set from 1 to k. So the goal is to select from J1 up to some J, we have a P, where P is at most n, such that the sum of S, maybe just write it, so Sj1, sum up to Sjp covers all the constants. K, not K. Yes, we have a number of sets and we want to do it. So now we have done all the combinatorics. This was not very simple, but still. After this, we still have a problem to solve. But now we actually know what is the problem to solve. I was actually surprised because there was one team at this contest, as I remember well, that solved only this problem. It was quite surprising for me because I don't consider this problem so easy. I don't know how. Maybe the team can explain themselves afterwards, but it was actually quite surprising. I think that there are some observations that you have to make to get it here. So now we have this problem of selecting just the sets here. And now we can recall the crucial condition that k times n is at most 400. Well, one could say this, so this is an NP-complete problem in general. And so if you try to, you cannot just solve it exponential time, at least during the contest. But like brute force approach here, like completely brute force, just some backtracking might not work here, or shouldn't work here. So you have to get smarter than that. But this condition actually is extremely important because this means that either k is at most 20 or n is at most 20. You cannot have both of them greater than 20. And this means that we have to have a solution that is either exponential only on k or exponential only on m. If we have such a solution, then we can just, so actually we will combine two solutions. From now on we have two cases. Either one is small or the other one is small. Well, they can both be small. And we want to find a solution that is fast in any of this, like a solution that is fast here and a solution that is fast here. And both of these solutions are quite simple and we have to just combine them. If k is at most 20, or maybe, okay, so maybe just first consider if n is at most 20. What does it mean? N is the number of topics, I guess, because oops. I have, like this, the original problem statement has kind of k and m swapped. You might have told me earlier. Now I got confused already. So, okay, so we stick to these denotations. However, the original problem statement had k was the number of topics and m was the number of contestants. I apologize for that. It was strangely written in the problem statement also. Okay, so maybe I can get rid of this before I get this not true. So if the number of topics is small, then it is very simple. I just choose at most m of the topics. So I just consider every selection of at most n topics, and of course at most m topics because there are not more than n topics. So at most, actually this is minimum n topics. And for such a selection, I just want to check if the sum of the corresponding sets is equal to 1 to k or not. So I just check if it covers everything. If it covers all the contestants. And I just check it by summing up. So this is 2 to the power of m. We have just all here we can just have all selections of any number of topics from these topics and just discard the ones that are wrong. And for each such selection, it takes me time proportional to m times k, I guess, because I need to check all the, so I consider all these guys here and I find what is their sum, the sum of these sets. Here you could also use bit masks and you could divide this by 32, but it was not necessary as far as I remember. can have k at most 20. So this is solution 1, then I have solution 2, and then I will combine these two solutions. So now we have a small number of contestants. And here it's a bit more tricky. And it actually introduces the topic that I wanted to then talk to you about half an hour. Is we have to have a large table. So we will have a dynamic programming here, but it will be indexed by one of the things that it will be indexed on is this case. So I would have, so for any like subset, so here will be a mask, and here will be an I. And what does it mean? I consider mask is a subset of contestants. So I have a subset of contestants, and I is the number of selected topics, of already selected topics, and assuming that I have selected this number of topics and this number of contestants, I want to well, I want to know if it is possible to achieve this number of I think it could be the number of the last selected topic. Yes. Yes. Number of the last selected topic. Actually, the second the second dimension, this dynamic programming will be implicit. We won't really store it because there's no topic. Last selected topic, and in such a case, we start. So this will be the minimum number of topics one needs to choose to cover the whole mask of contestants. Mask of contestants. So I choose T mask I topics out of the first I topics. I take their sum, and then I want to check if this is exactly the mask or not. And I want to take the minimum of it. So then what happens? When a new contestant comes, we just, so in this dynamic programming, a new contestant comes, so then to get to contestant topic I plus 1 comes. And when this topic comes, we say that therefore it has a subset as I plus 1. And what we do that for all masks, we take that T of mask sum as I plus 1 and of I plus 1 is the minimum of exactly this stuff and of T of mask of I plus 1. So in other words, to each such combination we try to add the subset S I plus 1 and we obtain a new mask and we just update the table. Actually the second, this is actually implicit, we can just this stuff. We will, it's implicit, we don't have to store it. So then the memory is 2 to the power of k, and the time is 2 to the power of k times the size of the, so times m, which is the number of topics. Because this is the size of the table, and we just compute each new element in constant time. So we see that we have these two complexities, to the power of k times something that is polynomial, and to the power of n times something which is polynomial. And what we do, we take the faster. So if I get some k and n, if k is smaller than m, then I select this solution, and if k is larger than n, then I select this solution. And from these two solutions, I take the faster one. So there are two nice tricks here. One of these is like this division. So if you see such a condition, then quite often it either means that the size of the whole input is not too large, and you can be like this often happens in problems where like multiplying two parameters would give you input data of size which is enormous. So sometimes just to say that this size of input data is enormous. But this was not the case in this problem. So the other thing that could be said is just that one of these two is not too large. And then you have to come up with a solution that is proportional to like the smaller one of these two. And here the nice trick was just that one of these solutions was very simple. Here you just iterate over everything. And here you have this nice dynamic programming with just for the given subset of topics. You would, so for the given subset of contestants, you want to find the smallest number of sets that you have to select. So I don't consider this problem very easy. And it was also created by the guy who is now one of the judges at the ACM ICPC, so it was nice to know about this problem. And at the last part of today's talk, I would like to say a few more words about solutions like this, so like algorithms like this won't surprise you anymore. This is the goal of the final part of today's class. So a few words about like dynamic programming on bit masks. This is how we call it in DP on bit masks. So here we will start with something that is even simpler than that, so that we can just have a complete view of what happens here. And we will analyze first a few problems in small graphs. So we will just devise what is the array, how does the table in the dynamic programming look like, and then from that we will somehow, and then we will come to a special family of problems that we will like to consider. So like part one, small graphs. So assume I have a graph with at most 20 nodes. This is a small graph. And I want to solve three problems for this graph. I want to solve the max cut problem. This is something different than the min cut. Here you have to find the maximum weight of a maximum number of edges on a cut, which is more difficult. I want to solve the matching problem. For the matching problem, actually, you have a polynomial time algorithm, but matchings in general graphs are hard. You quite different, like finding. So the graph is here; it's not weighted. So I want to find a perfect matching. Check if there is a perfect matching. So that everything is matched. And there is this traveling salesman problem. This is the first part. And how can we solve these three if the graph is small? So, what is max cut? I want to find, this is something a bit different than the min cut problem. So the problem max cut is I have the set of vertices, and I want to divide it into two subsets that have no common elements, so that the number of edges from V1 to V2 is maximum. edges from V1 to V2 is mask. And I know that the size of the graph is the graph is certain. So here this is quite a simple problem. You don't have to really store any particular table here. So what we do is just we can iterate over all V1s. So the solution is just to make a warm-up. Like iterate over all V1s. And we will store the V1 is actually a bit mask called mask. So it is just a single integer. So we store the subset as an integer from 0 to 1 to the power of n, so 2 to the power of n minus 1. So this will be a mask. Then I can have that V2 is, I take the mask that is everything, and I just XOR it with the mask. So then I have the set V2, I know which are the other guys. And then what I can check is I take for all elements of V1, so for all I in V1, which means I take just that this has to be in the mask. This means that this condition for all the elements of V1. What I can do is I take the number of elements, so the number of ones in the bit mask. I take the bit mask of V2, and I take it with the edges outgoing of the node 1. So actually, how can you implement this in the best way? So the best way to implement this is what we have already seen. This is like the graph will be actually, so how the graph looks like, the graph is just an array edges where n is the size of the graph. So then this graph is just an array of bit masks again. And then if I want to find the number of ones in a bit mask and edges of something, then the number of ones is just this built-in pop count. Here. So I take the built-in pop count and then I take the common part of these two sets. If you are fluent with bit masks, then this is fairly simple. If you are not, then maybe some of the tricks you might remember for later. So here the time of such a solution is I take all the subsets. So I take all the power of 2 to the power of n subsets. For each of them I take all the nodes in this subset. And then what I do, I just use built-in pop count, so that's all. So this is one of the basic applications. So first trick, you store the graph as an array of bit masks. So one in a bit mask means that an edge exists and 0 that it doesn't. And then for each, I iterate over all masks. Okay, so this was the easiest example for today. Then we have the matching problem. The matching problem is actually more interesting because, well, as I told you, if I have a general graph and I want to find if there is a perfect matching, there is a polynomial type algorithm. It uses some blossoms, it just changes these blossoms and so on. It's not very easy to implement. If you have it in the code library, then okay, you are done. If you don't, then we will show that you are not so screwed as you think that you are if you encounter such a problem. Because for the matching problem, this is actually one of the problems from very old years in topic-order competitions. You have just a small graph, you need to find the perfect matching. You don't care how fast is this algorithm as long as it is like not crazy fast. Slow, so for n at most 20 nodes you want to find the match.
Matching is not right.
Yes, it is. Yes, so it is polynomial. So polynomial type. However, the solution is hard to implement. So if you don't have it, you won't do it in 10 minutes. that one wasn't incomplete. This is not incomplete. You just want to find the logic and you want to have a simple algorithm for that. That works for small graphs. So here, there comes dynamic programming. And you want to have an array, whether it would be called is, yes, or maybe, yeah, or maybe is matching. Yes, so you have an array. Is there a matching? And this will be an array for all the masks, all the bit masks. So for each set of vertices, I would like to know whether there's a matching that matches this set of vertices. This is some idea. Yes. So for each subset of B, I want to know, is there a matching of this subset? This is actually the matching problem. So if I count this table, then the result is, of course, is matching in the array 1 and minus 1. This is the result, of course. The only question is how to compute this. Well, so this will be computed using dynamic programming. One way is a very simple algorithm that goes like that. And for all mask. So first of all, we start with is m of 0 equals true. There is a matching of zero nodes. And then for all masks from the smallest to the largest, what do? I have that. I only consider the masks for there is a matching. So if this mask can be matched, then I can try to extend this by a single edge. So I do for all ij such that I is not in mask, I will write it in this, and j is not in mask. Well, actually, normally you will have some bit operations for that. Yeah? So this means that mask and 1 to the power I, and you have not. This is actually how this you could write. So not mask and this. This is how you check it. So for each pair of such nodes, and such that there is an edge ij in edges of the graph, well, we can start. The graph is so small that we can just draw an adjacency matrix of this graph. So for each pair of such nodes, for each such situation, what do? We just say that this mask of mask. Then I add node I, then I add node j, and I say that it is true. And yeah, this is the whole solution. I don't do anything. So I have a mask, and I extend it by a new edge. And then I get a new mask for which I say that this is a mask, and then I will consider this new mask, and so on. Hope that this is more or less clear. So what is the complexity of this solution? How many steps are there? Yes. So we have 2 to the n times n squared. And there is a nice exercise for you. How can you get rid of that? Using this very approach. Any idea? Well, you have to consider all the masks. You have to get
I mean, and I'll even I always consider it's on the map.
so just to have no.
You only have to consider mass with another number of bits on
Yes, but how can you get better in time complexity? Not divided by 2.
You get the first bit in the mass over yes. Because the first bit, the first node in the mass have to find the edge.
Exactly. The idea is that you can take one particular I that is not in the mask, for instance the first one, and try to match it with anyone else. Because it has to be matched eventually because we're looking for a perfect match. Yeah? So we want to check if there's a perfect matching. So yeah, this is very nice, very good observation. So we just take for all. So the solution is the following. Here we insert, we remove I, we take I is not in the mask, just any such element. And then you take all j, such that, and then you do all the stuff. And this just decreases the exponent by 1 here. Because you can consider only one such element. So this is what statistics do. So this brings down the complexity even more. Well, still, if n is 300, then we are lost, but n might be, like, this might just suffice for the solution.
You have to mention how later or that element.
I? Yes, you can just iterate over all. Because you first find such I, and then you iterate over all j's. So this can be just done like brute force. You just go over all i's and check if it is in the mask. So this will be still in time 2 to the power of n times n. So this can be done. Well, there are some tricky functions. Apart from built-in hop count, there is this function we might have heard of. That is another built-in one. There is this built-in CTZ. We count trailing zeros in the mask. For instance, in the mask. So this is one of the ways you could try to get. So the trailing zeros are the leftmost zeros, least significant zeros. You count the number of least significant zeros. So then you have the first one, and if you negate the mask, you have the first zero. You want to check. So you could find this I using built-in CTZ. This is the second function out of built-in ones that I have ever used. But also you can just do it like by iterating over all such i's. You will get exactly the same efficient solution. Okay. And there is this third problem, the traveling salesman problem. And then we will get to the final family of problems. So the traveling salesman problem, I hope you more or less recall it. I want to find the cheapest Hamiltonian cycle in the graph. So the TSP is my cheapest Hamiltonian cycle. So a cycle that passes through all the nodes. And the cheapest means that there are weights on the edges. Or there can be weights on the edges in this problem. So this is a bit more tricky, however, this is the problem that is like very classic. That you really have to know it if you want to solve problems similar to these ones. And what is the basic idea of such a problem? First of all, because we want to find a cycle, Hamiltonian cycle, and the cycle actually doesn't have any beginning or any end because it's a cycle. However, we can choose the cycle to start in node 0. So you can just start in node 0 and go somewhere else. So this actually, because each Hamiltonian cycle has to pass through node 0, this means that we can cut this cycle into a Hamiltonian path. Yes? So we want to find the cheapest Hamiltonian path from 0 and then the cheapest Hamiltonian paths from 0 to all the other nodes and then extend them by one edge. So we find the cheapest Hamiltonian paths from 0 to all i's, all the other nodes, and extend each by the edge from I to 0. So this is a nice observation we can perform. And then to find the cheapest such path, we do exactly the same as previously. We will do dynamic programming on bit masks. It is always important just what is the bit mask. Actually, the bit mask, as in the previous problem, just some intuition. The bit mask stores something that we know we have already done, and we don't really care in what order we have done it. We just care what is the least expensive order. So here I would like to just start T of mass. It could be like the shortest, so the cheapest Hamiltonian path, the cost of cheapest Hamiltonian path from 0 that passes through all the nodes in mass. We don't care what is the order. All the nodes in mass. This is T of mass. But however, what is important for us, because we'd like to now extend this by a single new node, what is important for us is where this dynamic programming actually ends. So what is important for us is both the mass and the node I, so that ends in I. So we want to find that, so here it's any path, starts with 0, goes through all the nodes in the mass, and ends in the node I. This is exactly the state of the dynamic programming here. And then we can try to extend it. So from such a state, we can go to a new state. So the transition is from here to a new state, maybe this is the P1. So from here we go to T of mass or 2 to the power of j, ending with j. We can go here if, well, ij is in the edges of G, and this is plus the weight of the edge ij. So I could just go along the edge ij, and I can do it if this edge is here, and of course if mass and 1 to the power of j is 0. So we have this bit doesn't appear in the mask, and we can go extend this by this much. So these are the transitions in the dynamic program. So then, again, the crucial part is in the matching problem. We didn't care who is matched with whom, we just cared which set is currently matched so that we can extend it by one edge. Here we didn't really care who is after who in this partially constructed Hamiltonian path. We only cared which is the last one so that we can extend them. So it is always the case, and here we just get, well, if you use just brute force approach, you can have for n at most 10, you can just succeed. And if you have a bit mask approach, then the time complexity is like you consider all the 2 to the power of n bit masks. You have an additional additional dimension which is at most n, and we have at most n transitions from any of these two. So this is this very nice symmetric time complexity to the power of n and to the power of c1 extend this one. Very complicated. So this is some kind of a graphing, and it's important that you know this one. So now we know how to solve problems for small graphs, but the graphs can be small in a different way. And this is another very important thing that I like to say. Meaning there are graphs located on some narrow grids. And it's important to know how to solve these problems that we have already mentioned here on such graphs. So we'd like to solve the perfect matching problem and the TSP problem for graphs located on very narrow grids. What does it mean? So I have a grid. So given is a grid n times m, and n is small. At most, I don't know, 50, maybe at most 10. It depends on the particular. And n can be larger, however not that large. Yeah, let's say that n is at most 100. Let's consider the problem. Maybe both of these dimensions can be small, maybe not. And I have several fields of this grid are blocked. So we say that several of these are just, so you cannot really use these guys. And the first problem here is, can we cover the grid with 2 by 1 and 1 by 2 domino pieces? Can this be covered with 1 by 2 or and 2 by 1 domino pieces.
We saw this problem earlier in the Maratona last week.
Okay?
We saw this problem in the Maratona last week.
Ah,
The one of Mondrian.
okay. Congratulations. So we can consider this problem actually solved. And what was the time complexity?
I think, I don't remember, it was 2 to the n or something.
Okay, so this makes sense. Okay, so this was one thing because I talked to Rolf and other guys and they didn't actually know what was last week because nobody communicated what was the parts of the talk that were at this moment. Okay, so this is good that you know how to solve it. Okay. So maybe I just need a very short reminder of the solution because it is necessary to remember it for the second problem. Because the second problem is much more interesting and I don't think you might have solved it previously. So one of the solutions is that normally how you would like to, so I still won't really change too much the order of the talk. I just thought for 3 minutes just finish with this problem. So one thing is that you could actually select, so one approach that would be you just store the state, so you assume that all this stuff is covered, and here you have the state for each of the non-blocked fields. You could try to store if this field is blocked or not, so if it is covered or not, and you only could use domino pieces that were inside here. So you couldn't really cover anything here. So the state, one of the states that one could come out with would be for a given, for the mask that is here, mask, you would know so which ones are covered or not. Well, is it possible to achieve this using going from left to right? However, this is not good because if you want to extend it to the second row and then keep adding pieces here and here, then it will be very difficult to keep extending this mask. So what you can actually do is you can have a different kind of mask. This is how we solve it normally. So the mask will be these positions. For each of those positions, I can just check if it is covered or not. And if such positions are not covered, and then I will be extending, so for each of those positions that is not blocked, I have 0 or 1, meaning if I have already covered it or not. And I assume that everything here is covered already. And then I can extend it by this field. So this mask is extended right here. So here what I should do, I can either decide to cover it with such a domino block or such a domino block. And if this one is not covered, so if here is a 0 and it is not blocked, then I have to put the domino piece like that, and otherwise I can put it like that or like that, depending on if any of these fields is blocked or not. So here actually, here my type complexity is, I have 2 to the power of n masks. Mask is the sequence, so here is the mask, the sequence of bits here, and then I have the number of such positions here is n times m. So I don't know if you have something better than that, but this is what I normally do. So for
How do you know using that math when we are on a column and when we are on the previous one?
I just keep stepping, this mask just step by step. So I extend and move it by here. So the masks go like that. First I have the mask is a single column. Then I move the mask like this. So then the next mask is like this. Then the next mask is like this. Then the next mask is like this. So I always I keep enlarging this piece and shortening this one, and until I get to the next one, and I keep adding to the next column. So I just keep.
One of the means is that we are using that cell and assume if you want to use
Which cell? Well, I'm adding this cell.
cell, the one we are.
Yes, I am considering this. Okay, so maybe I consider this one, and I'm considering now this cell. So I have several options. If this cell is blocked, I don't do anything. I cannot. If it is not blocked, then I have several options. I can try to add a domino piece here. If this one was not blocked and not covered yet, I can add a domino piece here if this one was not blocked and not covered yet. And if this one was not blocked and not covered, I have to add such a block because otherwise I won't be able to won't be in the bit mask anymore. So everything that is not in the bit mask and is to the left of the bit mask, I assume that it was already covered. I hope that more or less this reminder helps you a bit. I didn't know that. It is actually quite lucky that it is, I think, maybe one of the first things that I have repeated comparing to the first week. Or maybe not, but you didn't tell me earlier. And the final problem that I would like to consider with you in a few more minutes is the TSP, traveling salesman problem. It's just, for me, it's just, maybe it might not be just TSP. Maybe let's make it even easier. I just want to know if there is a Hamiltonian cycle. I would like to know this. If I can go with a Hamiltonian cycle on this, maybe if it's the cheapest one, maybe there's something else. There are quite a lot of problems at the ICPC finals. At least there were a few in Harbin, China. I think there were at least 2 problems which is something of similar flavor to this one. And almost no team solved it, so solve these problems. But at least one of them was approachable, totally approachable. You could have a similar stuff if you have a similar thing that will be as homework, let's say more or less, is the minimums, the spanning tree. Yeah, so for instance, counting spanning trees of the graph. So you see that the graph is just the non-block nodes, and the edges are just adjacent nodes all the time. So here I can either find a Hamiltonian cycle, count Hamiltonian cycles, count whatever Hamiltonian cycles. So the approach here could be similar, yes. One could think that, okay, so I have this last bit mask, whatever, yes, and for each of those nodes I would store something. The question is, what is something? So I will have a partial solution all the time. So I want all these fields to be, so I assume that everything here again is covered, whatever it means. But what is a Hamiltonian cycle? It is a cycle that goes through all the nodes. Which means that, first of all, it has to cover all the nodes, but it has to be one connected component. It cannot be, well, you cannot cover, if you do it the wrong way, you could cover all the nodes like this, and this is not the Hamiltonian cycle. So if you cut it like this, then the Hamiltonian cycle will be actually a set of, maybe I'll remove this cover, will be a set of paths. You cannot have a closed cycle here, this is not possible, but you might have a set of paths. So there's one path, starting here and ending here. There's another, starting here and ending here. There's another, starting here and ending here. And a path here. So what we could store is that we could store which of these positions, maybe there's a path, okay, this will also go here, yeah? So this path might end like that. So one thing that we could imagine to store is to store which of these positions, well, which of them are not covered yet, so if one of them would not be covered, that would be bad. But which positions are endpoints of such paths? So you could just store that here is a 1, 1, 1, 1, 1, 1, 1, and 1. However, this doesn't give me the information who is connected with who. If I know that here are ones, then I could either have it this way or have it this way. And note that these two situations are totally different because, for instance, this black part can be connected this way, however, this blue part has to be connected this way. So their extensions are totally different. So you can't only store these once, it's not sufficient. We have to add information. We have to remember which endpoint is connected with which other endpoint. So we just remember that this guy is connected with the guy number 8, this guy is connected with the guy number 3, this with guy number 2, this with guy number 7, 6, 5, and so on, and 4, and 1. So I could store such information, for instance, who is connected with who. And then I will be trying to extend this, so I first of all check. So, and zeros mean that I'm not an endpoint. Not an endpoint. Yes. So I can try extending such big masks. It requires some more consideration to, like, I leave this for you just to think a bit how to, like, extend these states. However, one question I'd like one could ask is, what is the number of such states? Normally, if you just have bit masks, there are 2 to the power of n states, we are going to so simple. Here, it looks like it is exponential, it looks, I don't know, factorial of n, whatever it looks like. Very bad. Is it so bad? Is the number of such states that we know? Actually, yeah, so we have, so how many states are there where there are, for instance, 2k endpoints? So I have 2k endpoints, and I remember how are they connected actually? And I would store how are they connected? How they are. And a very nice observation that is not trivial is that the number of such ways to connect is not very large. It will be, have you ever heard about Catalan numbers? So Catalan numbers are the number of correct ways to set n pairs of brackets. So here I have k pairs of brackets. And yeah, because this notation shows that this is one is an opening bracket, opening, closing, opening, opening, closing, closing, closing. This is exactly a sequence of brackets. And if I have such a sequence of brackets, then I have a sequence of k brackets. So this means that this is not greater than the number of such configurations is not greater than the k Catalan number. And this is, this was something like 2k over k divided by k plus 1. So this still looks mysterious, however it is good to know that this thing can just be bounded by 2 to the power of 2k, because it's not greater, because like the sum of all those such guys over all these lower components is 2 to the power of 2k. So actually this is not as bad as one would think of. The story, so I have to store this way how this stuff is connected. So it's not that simple as storing a big mask. However, I don't have to. Like. It's not like k factorial or whatever. It's not that bad. And then we can somehow think of extending these masks. Some people just extend it by one, like from here to another. One could also rethink this idea. So this is the most complicated part of today's analysis. I cannot really continue about this because first of time constraints and then it's a bit technical. And one good piece of advice for each team that sees a problem like this, similarly for like spanning trees. For counting spanning trees, you also have to know whether the parts are already in the same connected component or not. Well, there you can also have, so there you can also have to store in which connected components are the respective parts. And just a good piece of advice, if you want to try to solve it during a real contest, and you have never solved any problem like that, then most probably you won't succeed. So it's good to try to solve at least one such problem just beforehand, just on a training session, before you try to solve any, like I'm talking about like such problems with these connected components that we have to solve. Because it's nice to talk about, and it's very convenient just to say in a few minutes, okay, so you do it like that. But if you like come to real coding, then it's not that nice to have such a piece of code. Okay, so this, like the official part, we're getting to the very end of the official part of the last lecture. I know that like during these lectures, well, first of all, not everything was like explained very clearly and very slowly. My goal was more to stimulate you a bit, like to show some different ideas, show some styles of thinking, show some new kinds of problems. Maybe some of this was, I wasn't really talking too slow. I was like supposed to be like moving in a quite high pace, so I hope that you didn't really mind that. Maybe not everyone could understand everything in this pace, but I hope that there's at least some of this stuff that you could remember. And many teams told me, asked me how to train for the world finals, for instance, for the competitions. And I have given people many different answers. Some of the answers, of course, you have to train on the World Finals problems, but not only. There are these World Finals warm-ups that are also a nice type of contest on this Valladolid online judge. They are also a nice thing you can train on. However, there are also, at least we encourage our students in Warsaw to participate in all these important individual competitions, like Google Coach Jam, like Top Coder Open, because you can try to stop. Okay, so you can think, okay, so I go to this like on a live archive of ICPC, and there are like zillions of regional contests, like 20 World Finals contests, and so on. But you have to take into consideration that there are some trends in problems. When I competed in Top Coder several years ago, now I just do it from time to time, the problems were completely of a different nature. They were just completely different kinds of problems. Some of them were parsing problems, some of them were nice algorithmic riddles, however, they were very different. Then came another main problem setter. He changed totally. Now it's Makoto Sajima, who has yet even more different approach. Now we have problems which are just algorithmic and totally out of the box, with usually some very short solutions which are very difficult just to come up. So there are some trends. The same happens at the World Finals. The tasks that were there 10 years ago are completely different than the tasks that are there here. Many of the judges of the ICM ICPC work at Google. So they just organize Google Coach, and there are the problems created by the same guys. And this is just good to compete in the contests which are up to date, because they show the current trends of how the problems look like. I see that I've competed for several years in such competitions. I see that the trends really change. You can also compete in Code Forces, in Facebook Hacker Cup if you already started this year, but still, I think that contests like Google Code Jam, Top Coder Open are the crucial ones, and they're good for individual training. And you have to just stay up to date with the problems that there are already there. So this is one other piece of advice how to train. And also at the conclusion of the classes, I have a small gift for you. I wonder where so this is a number of pages. Yes. So from at several classes, and at some point I told you, okay, so if you want, you can solve at home this and this problem. So this is like a nice exercise. And from these classes I have proposed a series of 5 plus 5 problems. And the challenge is to try to solve these 5 problems. All these problems are in the main website, and the rank list that you usually had during the contest to track the rank list, not yesterday but all the previous days. There is the same rank list with all these problems, and these problems are divided into 5 parts. So there are 5 problems related to the classes that were here. So problem from class 1, problem related to class 2, to class 3, and up to class 5. These are a bit more difficult. They are not very difficult, but they are related to the stuff that we are talking here about. So you can try to check did you get everything. They are not very trivial, you just don't apply straightforward the techniques that were here, but they are very similar to the techniques that we have developed here. On the other hand, if you don't like applying known techniques, there are some contestants who just like to think out of the box. Then I proposed 5 other problems. The solutions to these problems don't require actually any techniques, particularly techniques more difficult than BFS algorithm, whatever. Just very simple stuff, but you have to just come up with the idea. So these are the algorithmic riddles that I tried to propose also during this week, because we also normally train for such problems very often. So we have this problem, just come up with the solution just from nowhere. You can think for 1 day, for 2 days, and sometimes people the 3rd day or the 4th day they just get the idea, and they are extremely happy when they do it. And they are also not that difficult. So there are no killer problems in this set. That's just a challenge for you until the end of February. There's this date written here, and it is also on the website, to try to solve at least 5 problems. I will be tracking all the logins that you gave me during the team contest or the individual contest. You can, it is designed for individual solving, but you can also solve it in teams. And I strongly encourage you to try to solve these problems. I will be monitoring your progress. Maybe the rank list is not working yet, and almost set up, so it will be there. So I just give it to you, maybe I'll just put it near the exit of the class, and I thank you very much for the attention, and good luck. contact. And today's and last individual contest, nice problems for today. So